Hey guys, welcome back to the machine learning course for beginners by Uplatz. So in the previous lectures, we have completed the k-means algorithm and KNN algorithm for clustering, right? So in this lecture, we will start a new type of clustering called the DBSCAN clustering, okay? So the DBSCAN stands for density-based clustering. Okay, so it has a full form with noise. Okay, density based scanning clustering applications with noise. So this is the full form of DBSCAN. Okay, so as you know, clustering analysis is an important problem in data analysis. Data scientists use clustering to identify malfunctioning servers, then group genes with similar expression patterns and perform various other applications. So there are many families of data clustering algorithms, and you may be familiar with the most popular one. So we have done k-means, right? So k-means determines k centroids in the data and clusters points by assigning them to the nearest centroid. So we have done this in the previous lecture, right? And since while k-means is easy to understand and implement in practice, the algorithm has no notion of outliers. So all points are assigned to a cluster even if they don't belong in any. Correct? So in the domain of anomaly detection, this causes problems as anomalous points will be assigned to the same cluster as normal data points. So it's a very alarming situation. The anomalous points pull the cluster centroid towards them, making it harder to classify them as anomalous points, correct? So it's a very serious issue we need to overcome. So in this lecture, I will cover a family of techniques known as density-based clustering. Compared to centroid-based clustering like k-means, density-based clustering works by identifying dense clusters of points, allowing it to learn clusters of arbitrary shape and identify outliers in the data. In particular, we will discuss the highly popular DBSCAN algorithm. Okay, then we use the implementation of DBSCAN algorithm using Python. So let's begin. So you can see that preliminary we want some topics to be understood for carrying out the DBSCAN. Okay, so before we can discuss density based clustering, we need first to cover a topic that you may have seen in a topology course, that is the Epsilon neighborhoods. The general idea behind Epsilon neighborhoods is given a data point, we want to be able to reason about the data points in the space around it. Formally, for some real valued epsilon greater than 0 and some point p, the epsilon neighborhood of p is defined as the set of points that are at most distance epsilon away from p. So when I show you an example, you will understand what is this. So if you think about geometry, right, the shape in which all points are equidistant from the center, so you can easily tell me that the shape is circle, right? In a 2D space, the epsilon neighborhood of a point P is the set of points contained in a circle of radius epsilon centered at P. In 3D space, the epsilon neighborhood is a sphere of radius epsilon centered at P. And in higher dimensional space, the epsilon neighborhood is just the n sphere of radius epsilon centered at P. Okay. So let's consider an example to make this idea more concrete. So see this diagram, what I've shown you. We have scattered 100 data points in the interval 1,3 to 2,4. So the x-axis is 2 to 4 and y-axis is 1 to 3. So let's pick a point 3,2 to be our point P. So you can see a blue point which is at the coordinates 3,2. So this we call it as point P. Now what we do? First, let's consider the neighborhood of P with radius 0.5. Okay, so let's imagine our radius to be 0.5. So here the epsilon becomes 0.5. The set of points that are distance 0.5 away from P. So when we consider radius as 0.5, we see set of points that are away by 0.5 distance from P. So what are those points? So you can see the next picture. Okay. So here you can see the opaque oval represents our neighborhood. So when we take epsilon equals 0.5, then we cover this opaque green oval or blue oval. This represents our neighborhood, that is the points which are 0.5 distance away from point P, that is the blue point. And you can see, if you count, there are about 31 data points in this neighborhood, correct? So just you can have a look. We have 31, around 30 or 31 data points in the distance 0.5 from the point P that we have represented as the oval. So since we scattered 100 data points and 31 are in the neighborhood, this means that a little under 1/3 of the data points are contained within the neighborhood of P with radius 0.5. So out of 100, if we have 30 points in the neighborhood, we can say that 1/3 of the data points are contained within a neighborhood of P with radius 0.5. Now what we do? Now let's change our radius to 0.15. Before it was 0.5, now we will change it to 0.15. That means the epsilon becomes 0.15. And consider the resulting smaller neighborhood. Now let's go to the next image. Okay, so here you can see when we change the epsilon from 0.5 to 0.15, we have shrunk the neighborhood. So now only 3 data points are contained within it. So what does it mean? By reducing the epsilon from 0.5 to 0.15, which is around 70% reduction, we have decreased the number of points in our neighborhood from 31 to 3 data points. So it is 90% reduction in the density of the neighborhood, correct? Now that we have defined what we mean by neighborhood, correct? So I guess the concept of neighborhood is clear to you. Next, we will introduce the next important concept, the notion of a density for a neighborhood. So let's begin. So just imagine in a grade school science class, the children are taught that density equals mass divided by volume. Let's use this idea of mass divided by volume to define density at some point P. If we consider some point P and its neighborhood of radius epsilon, we can define the mass of the neighborhood as the number of data points contained within the neighborhood, and the volume of the neighborhood is volume of the resulting shape of the neighborhood. In the 2D case, the neighborhood is a circle, so the volume of the neighborhood is just the area of the resulting circle. In the 3D and higher dimensional case, the neighborhood is a sphere or n sphere, so we can calculate the volume of this shape. So for example, let's again consider our neighborhood of point 3, 2 of radius 0.5 again. So the mass of the number of data points in the neighborhood is 31, correct? So the mass is 31. The volume is the area of the circle, that is pi r square, correct? So we have the radius as 0.5, the square becomes 0.25. So that means volume equals pi multiplied by 0.25, which is pi divided by 4, okay? Therefore, our local density approximation at p equals 3, 2 is calculated as density equals mass divided by volume. So we have mass and we have volume, which is 31 divided by pi by 4, which is 124 divided by pi, which is approximately equal to 39.5. Okay. So this is the density we got by calculating the mass divided by volume, which is around 39.5. This value is meaningless by itself, but if we calculate the local density approximation for all points in our data set, we could cluster our points by saying that points that are nearby and have similar local density belong in the same cluster. So I repeat, if we calculate the local density approximation for all points in our data set, we could cluster our points by saying that points that are nearby and have similar local density approximations belong in the same cluster. If we decrease the value of epsilon, we can construct smaller neighborhoods that would also contain fewer data points. Ideally, we want to identify highly dense neighborhoods where most of the data points are contained in these neighborhoods, but the volume of each of these neighborhoods is relatively small. So while this is not exactly what either DBSCAN or level set tree algorithm does, it forms the general imagination behind the density based clustering. So we will see an example for a better understanding. So now let's see the DBSCAN, which stands for density based spatial clustering of applications with noise. Okay. So DBSCAN is the most well-known density-based clustering algorithm. It was first introduced in 1996. Due to its importance in both theory and applications, this algorithm is one of the best algorithm in machine learning clustering. Unlike k-means, DBSCAN does not require the number of clusters as a parameter. Rather, it infers the number of clusters based on the data, and it can discover clusters of arbitrary shape for comparison. And as we have seen earlier, the epsilon neighborhood is fundamental to DBSCAN to approximate local density. So the algorithm has two parameters. So the epsilon, that is the radius of our neighborhoods around a data point P, is epsilon, and minimum points, the minimum number of data points we want in a neighborhood to define a cluster. Okay, so these are the two very important terms or parameters. The first is the epsilon, the second is minimum points. So using these two parameters, DBSCAN categorizes the data points into three categories. So the first category is the core point, then border point, and the outlier. Okay, so this is a very important step. So what is a core point? A data point P is a core point in neighborhood if it contains at least minimum points. Okay, so we define the value for the minimum points. So the core point is a data point in the if the neighborhood contains at least the minimum points. Okay, so that is known as core point. Then what is a border point? A data point is a border point if the neighborhood contains less than the minimum points, but Q is reachable from the core point P. Okay, so I'll repeat. The border points is a data point Q. Okay, so the core point is a data point P, whereas the border point is a data point Q if the neighborhood contains less than the minimum points, but this Q is reachable from some core point P. Okay, so that becomes a border point. Then what is an outlier? A data point is an outlier, so we denote it as O. So a data point O is an outlier if it's neither a core point or a border point. So if it is neither a core point nor a border point, we call it as an outlier. We denote it as O. Essentially, it is the other class. Okay. So these definitions may work very importantly in the DBSCAN algorithm. So first, let's understand core points. Core points are the foundations for our clusters, are based on the density approximation. We use the same radius to compute the neighborhood for each point. So the volume of all the neighborhoods is the same. However, the number of other points in each neighborhood is what differs. So just recall that I said we can think of the number of data points in the neighborhood as its mass, correct? The volume of each neighborhood is constant and the mass of neighborhood is variable. So by putting a threshold on the minimum amount of mass needed to be a core point, we are essentially setting a minimum density threshold. Therefore, core points are data points that satisfy a minimum density requirement. Our clusters are built around our core points. So by adjusting our minimum points parameter, we can fine tune how dense our clusters cores must be. Okay. So I repeat, core points are the foundations for our clusters since they're based on the density approximation. We use the radius to compute the neighborhood for each point. So the volume of all the neighborhoods is the same. However, the number of other points in each neighborhood is what differs. And we know that the number of points in the neighborhood is called as mass. The volume of each neighborhood is constant and the mass of the neighborhood is a variable. So our clusters are built around our core points by adjusting our minimum points parameter. We can fine tune how dense our clusters core points must be. So next is the border point. So border points are the points in our clusters that are not the core points. In the definition for the border points, I used the term density reachable, correct? So I have not defined this term yet, so we'll define it now. But the concept is very simple. To explain this density reachable topic, let's take this picture, what's appearing on the screen. We define our neighborhood with radius 0.15. Okay, so consider the point R, that is the black point, that is outside the point P's neighborhood. So here the point P is the core point okay, with radius equals 0.15, and we are considering a new point, that is point R, which is the black point. This is outside of the point P's neighborhood, correct? Because the point P's neighborhood has only 3 dots, 3 points. The black data point is outside the point P's neighborhood, okay? So all the points inside point P's neighborhood are said to be directly reachable from P. So you can directly reach those 3 points from P, correct? Now let's see the neighborhood of point Q. So we have point P, that is blue point, and point R, that is a black point. Now we have another point Q. So we will explore the neighborhood of point Q. A point, this Q point is directly reachable from P. So let's scroll down. Yes. So you can see here we have defined one more point Q. This point is directly reachable from P. You can see a yellow circle. It represents the Q's neighborhood. Okay, the yellow circle represents the Q's neighborhood. Now what is it? Now, while our target point R is not our starting point P's neighborhood, but it is contained in point Q's neighborhood, correct? So when we go up, you can see here point, the black point, that is point R, is not reachable from point P. But when we define a point Q, and when we define its neighborhood, you can see that the point Q is directly reachable from point P. But the point R is not directly reachable from point P, but the R is not our starting point, P's neighborhood, but it is contained in a point Q's neighborhood, correct? So it is contained in point Q's neighborhood. So this is the idea behind the density reachable. If I can get to the point R by jumping from neighborhood to neighborhood, starting at a point P, then point R is density reachable from point P. So this is the meaning of density reachable. So as an analogy, we can think of density reachable points as being the friend of a friend. If the directly reachable of a core point P are its friends, then the density reachable points in the neighborhood of the friends of P are the friends of its friends. One thing that may not be clear is density reachable points are not limited to just 2 adjacent neighborhood jumps. As long as you can reach the point doing the neighborhood jumps starting at a core point P, that point is density reachable from P. Okay. So friends of a friend of a friend of a friend are included as well. Okay. It is important to keep in mind that this idea of density reachable is dependent on our value of epsilon. By picking larger values of epsilon, more points become density reachable, and by choosing smaller values of epsilon, less points become density reachable. Okay. So I'll repeat. The idea of density reachable is dependent on our value of epsilon. By picking larger values of epsilon, more points become density reachable. And by choosing smaller values of epsilon, less points become density reachable. Then outliers. Finally, we get to our other class. What is the outlier class? The outliers are points that are neither core points nor are they close enough to a cluster to be density reachable. from a core point. Outliers are not assigned to any cluster and depending on the context may be considered as anomalous points. So this is the detailed explanation of density-based clustering. So DBSCAN is implemented in the popular Python machine learning library scikit-learn, and because this implementation is scalable and well tested, it works good. Okay, so in the next lecture, I will show you how to implement the DBSCAN algorithm using Python. All right. So any doubts, you can mail us. Just go through the lectures again and try to understand the concepts. All right. Thank you.